Welcome back to Protovenix Verilog Masterclass. Now that you understand design hierarchy, it's time to start coding. In this episode, we'll explore the basic concepts of Verilog HDL, the building blocks of every digital design. Lexical conventions are the grammar rules that Verilog follows, how we write code so the compiler can understand it. Verilog is case sensitive, and keywords are always in lowercase. White space separates tokens but is otherwise ignored, except within strings. Comments, essential for code readability, come in two forms: single line with and multiline with asterisk and asterisk. Numbers can be specified in decimal, hexadecimal, octal, or binary format using the size for base format or number structure. Identifiers or variable names can be up to 1024 characters long, starting with a letter or underscore. Proper naming, indentation, and commenting make your Verilog code easy to debug and simulate. Verilog supports different data types to describe signals and storage elements, crucial for accurate hardware modeling. There are two main groups: net data types, representing physical connections, and variable data types, which store values. Wire represents continuous connections, much like physical wires, and must be driven by a data source. In contrast, rec stores values inside procedural blocks like always or initial, holding its value until explicitly changed. Integer is a 32-bit signed variable, ideal for counters and loops, while real is used for non-integer calculations in simulation. Finally, time stores simulation time values, represented as a 64-bit variable, crucial for timing analysis. Verilog also uses a 4-state value system: 0, 1, X for unknown, and Z for high impedance, allowing for comprehensive circuit modeling. Choosing the right data type ensures your simulation behaves exactly like real hardware, reflecting its true functionality. System tasks are predefined Verilog operations that help you control simulation and display information, starting with a $sign. $display prints output to the console, providing immediate feedback during simulation. $monitor tracks signal changes and displays their values, continuously updating whenever a change occurs. Only the last $monitor statement invoked remains active, ensuring focused observation of specific signals. Other system tasks include file I/O for reading and writing data, timescale tasks for defining timing, and simulation control tasks like $finish to stop the simulation. $display prints output, $monitor tracks signal changes, and $finish stops the simulation. These are super useful when debugging your design behavior. Compiler directives give special instructions to the simulator or synthesis tool. They start with a backtick. The include directive adds external Verilog files, promoting modularity and code reuse. Define defines constants or macros, allowing for flexible parameterization within your code. Timescale sets the time unit and precision for delays, like timescale 1ns 1ps, defining the simulation's timing granularity. If def endif enables conditional compilation, where code is compiled only if a specified macro is defined, useful for different configurations. Directives make your Verilog code flexible and reusable, especially in large projects adapting to various design requirements. So to recap, lexical conventions define how we write Verilog, data types define how signals behave, system tasks help us simulate and debug, and compiler directives give power to our code. Mastering these fundamental concepts is your first step towards designing complex and efficient digital systems. Keep practicing,